Hi, I'm Jack Baker. In this video, I'm going to discuss my group's research on spatial correlation and ground motion intensities, discussing the measurement, prediction, and implications of these correlations. This work was presented as the 2023 William B. Joyner Lecture at the annual meetings of the Earthquake Engineering Research Institute and Seismological Society of America, and I'm recording it here to provide online access for those who weren't able to attend those meetings and hear the talk live. Before I get started, I'd like to thank the many folks who contributed to this work over almost 2 decades now. In particular, Lucas Bodenmann's work will be highlighted in the second part of the talk, but a number of former students played really important roles in this, and some of their work will also be highlighted. I'd also like to thank the many collaborators listed at the bottom of the slide who provided insights or data or expertise and support in getting this work out into the world. Okay, so to get started, let's first discuss what exactly spatial correlations and ground motion intensity are. So here, this map shows a plot of observed ground motions from the 1999 Chi-Chi, Taiwan earthquake. This is I'm plotting 1 second spectral accelerations, so one metric of ground motion intensity. The same analysis could be repeated for other measures of ground motion intensity. So this, the white area shows the island of Taiwan. The gray rectangle shows the surface projection of where the earthquake rupture occurred in this earthquake. And then each circle on the map is showing a location of a ground motion recording instrument that recorded the shaking. And those circles are colored according to the intensity of ground shaking. So the darker colors are stronger intensity of shaking. And we see that nearby the earthquake or above that surface projection of the earthquake is where the strongest shaking tended to occur. And at more distant points on the island, the shaking was less intense in general. So let's break this down a little bit more in detail. So the left pane here shows the same map as the previous slide. So these were the observed ground motion intensities. A lot of this pattern we can predict using a ground motion model. So here I'm using an empirical ground motion model in the middle panel. And these are the predictions of the ground shaking intensity we would expect to see. So that was a function of the magnitude of the earthquake, then the distance from the rupture to the station. So you can see that the predicted intensities tend to decrease as we move away from the rupture. And also that prediction model includes things like soil conditions measured via shear wave velocity over the near surface portion of the site, VS30 value, for example. And so we see in this middle map, this tendency for the amplitudes to attenuate with distance. And so we get further away and we get to less intense motions, although there are some patches where the predicted motions are a little more intense due to local site conditions. So the difference between the observations and the predictions, and we do this with a log transformation and some other details, but basically the prediction error is shown over on the far right side, and this is what we call a within event residual. And so this is a metric of the observation minus the prediction, again in log space. And there's an extra between event residual that's subtracted out as well, not too important for today's discussion. So here, the blue points on this right panel are showing areas where the predicted intensity was larger than the observed intensity, so that the residual is negative. And then the red coloring is showing places where the observed intensity was stronger than the prediction. And so these are model residuals. This occurs in lots of different engineering and science models where our predictions and observations are a little different than each other. And so what's important here, though, is that these residuals are not independent from station to station. So it's not that each station has this random residual. We see the spatial clustering of these residuals. So say to the west side of the island, west of the rupture, we have this clustering of all these blue residuals where kind of throughout the region, the ground motion intensity was less intense than predicted by that ground motion model. Or up at the north part of the island, we have this big clustering of all these red residuals. So these are all places where the ground shaking was stronger than predicted. And it's these spatial clustering of these residuals that we're going to dig into in more detail in this video. So those correlations in residuals are not surprising from a physical perspective. There's lots of reasons why we would expect to see this. So one is, the rupture is just shown here as this rectangle, but it's not kind of a uniform rupture in terms of the energy released or the amount of slip from point to point. So there's points on that rupture that are releasing more energy, so-called asperities, and stations that are nearby those asperities would tend to all have higher strong ground motion intensities, or away from asperities you might have weaker than predicted ground motion intensities. There's also an effective wave propagation path. So if there's anything in the crust that's tending to focus waves or deflect those seismic waves away from a site. Stations nearby each other are going to tend to have similar wave propagation paths and thus similar deviations of their observed intensity relative to predictions. And then another effect that's important is local site effects. So I mentioned the predictive model is going to use this VS30 parameter to measure site conditions, but the effect of near-surface geology is rather complex on whether ground motions will be strong or weak relative to some predictive model. That predictive model is only going to have an imperfect characterization of those site conditions. If there are other unexplained factors in those site conditions, and if those factors tend to be consistent from location to location in a region, that will again manifest itself in spatially correlated residuals, as we see here. Okay, so we expect to see this for physical reasons. We do see it empirically in observed ground motion data. And so that's our first kind of consideration here, just getting some basics. These correlations are of practical importance. A couple ways to think about that. First of all is with regard to earthquake reconnaissance. So here I've got a plot of the ShakeMap produced by the U.S. Geological Survey for the magnitude 7.8 earthquake that occurred earlier this year in Turkey. The triangles here are showing locations of observed ground motion intensity, similar to the circles on one of our opening figures. The lines are showing the surface projection of the rupture, kind of coming through the middle of the figure. And then the colored contours are contours of predicted peak ground velocity, the metric of ground shaking intensity in this map. And those contours are produced using ground motion models to predict kind of expected amplitudes, and then using those stations with some spatial interpolation, understanding the correlation to infer kind of deviations from the ground motion model in space. I'll note this Warden et al. Paper for some of the analysis details, but these contours are taking into account that spatial correlation we've just been discussing. Another way in which these correlations matter is when we're doing simulations of regional risk for potential earthquakes that haven't yet occurred. So here I've got some maps from some former work of Mahalia Miller. And what we were doing when we were looking at infrastructure risk or regional risk is in this left panel, we've got a simulation of earthquake ground motion for a possible future earthquake rupture. Here now looking in the San Francisco Bay Area. So the black line here is the surface projection of a potential future rupture. The coloring in this map is the ground shaking intensity, again measured via 1 second spectral acceleration. And this is varying in space. It's reflecting the attenuation of amplitudes with distance from the rupture. It's reflecting site conditions, and it's also including spatial correlations as we've started to discuss. For that map of ground shaking intensity, we then come over in the middle panel and look at damage to assets of interest. So in this case, it was highway bridges. And so the locations of all those bridges are shown with circles. And then the red circles are indicating bridges that were simulated to have been damaged given this earthquake scenario. And so that damage is occurring as a function of ground motion intensity. Then once we have these damaged bridges, we can do a simulation of the transportation network. That's the right panel. And taking all of the users of the transportation network, trying to get from origins to destinations, and having to reroute around bridges that were severely damaged. That's going to cause extra traffic and congestion. And so we compute the travel time increase associated with that rerouting and congestion from the bridge damage. We then take this type of analysis process, run it thousands of times, simulating a range of possible future earthquakes in the region and the resulting ground motions and damage that could occur. And we get a plot that looks like this. So the horizontal axis of this plot is the consequence metric that we were studying. This is, in this case, is travel time delay, so the total travel time delay for all of those users of the network. So heading towards the right means we've got kind of more travel time for all those users due to this disruption. And then the vertical axis is the annual exceedance rate of that level of delay. And we get these annual exceedance rates by taking all of those simulated maps of the type on the previous slide and counting up how many of those maps had caused some level of travel time delay or greater. And then we count how often those maps are projected to occur, given what we know about occurrence rates of future earthquakes and things like that. So we see that the small levels of travel time delay are occurring frequently, so with higher annual exceedance rates. And as you get out to larger travel time delays, those are more and more rare because it's only the very rare outcomes that can produce that level of disruption. Okay, so this black line is our best estimate given our best characterization of the earthquake ground motions, the spatial correlations, and then the functionality of the road network. We then repeated this analysis using some different assumptions about the ground motion amplitudes. So the top line is, again, our best estimate with that spatial correlation. We reran exactly the same analyses, holding everything the same, except taking out the spatial correlation in those residuals. So rather than having those residuals of the ground motion amplitudes be spatially correlated, we just simulated independent residuals at each location of interest. So the variability is still there, just not that spatial correlation. And the line comes down. And then I'll note, I guess, the final line is if we take off the ground motion variability, we just assume that the ground motion amplitudes are the median prediction from the ground motion model, the line comes down even further. So what's going on here? We could kind of work from bottom back up, I guess. If we don't include ground motion variability, we don't consider the possibility that the ground motions could ever be stronger than predicted. And so we don't ever have the kind of extreme outcomes of ground motion amplitude that cause the large levels of loss. And that's why the consequences get capped at a smaller number here. We also don't ever predict weaker than predicted ground motions. And so that has some effect on the very small consequences becoming more likely, but that's not as interesting to us from a risk analysis perspective. The red line's the interesting one here, I think, for the topic of today's discussion. So if we leave off the spatial correlation, we still consider the possibility of stronger than predicted ground motion amplitudes, but they are not spatially correlated. And so what happens is that at a particular location with a bridge, we on occasion sample these strong ground motion amplitudes and the bridge is damaged, but there's some rerouting path nearby that travelers would take instead. And when we don't have spatial correlation, that the bridges on those adjacent redundant paths are less likely to have the strong ground shaking, and so the rerouting paths are more likely to be available. When we do include the spatial correlation in that blue line, when we have strong ground motion at one location that damages a bridge, the surrounding locations are all also more likely to have strong ground shaking, and so the redundant paths are more likely to be damaged, meaning that we need kind of longer paths around those damaged zones for the users trying to get through the area. And so we have this possibility of very large consequences due to these kind of regions being disrupted, causing clustered bridge damage and more difficulty with congestion and rerouting. So when we're thinking about these kind of upper tail probabilities and extreme outcomes that we'd like to avoid, these spatial correlations are important in these types of problems. Similar patterns can be seen when you're looking with insurance companies looking to insure portfolios of properties located, distributed throughout a region. For them, for the same reasons, they need to worry about these spatial correlations because it induces correlations in the losses to all those properties, and you have an increased chance of these high upper tail outcomes occurring. Okay, so those are a couple of quick examples of why the spatial correlations matter in these types of problems. So now let's talk a little bit about estimation of spatial correlations, right? We see these patterns like in this map on the right that I've shown a few times, and we'd like to take that data and then estimate, what do the correlations look like? I actually already used, some estimated spatial correlations for those results shown on the previous two slides. Let's talk for a few minutes about how we do that. So ideally, what I would like, if I was trying to estimate correlations at a pair of these locations on the map, is that I would like to have multiple observations of ground motion amplitudes and residuals for each station pair. And then I could look over these sets of data or sets of earthquakes and see how correlated do those two pairs of stations tend to have in their, how correlated are those stations residuals. That's really practically not possible because it would mean we need to have a number of strong earthquakes in order to gather that, and there's only a few places where we've got data of that type. It also wouldn't do us any good for estimating correlations at locations where we don't have ground motion instruments because we don't have any sort of data. So what we do instead, for practical reasons, is we are going to assume that this correlation in ground motion intensities is only a function of the separation distance between the stations, all right? And that any pair of stations with the same separation distance is going to have the same correlation. So this is what we call an assumption of stationarity. So the idea would be that if I'm looking for a correlation between two stations with a given separation distance, I'm going to find all the pairs of stations with that separation distance and pool those paired observations together to make my collection of data I can use to estimate correlations. And that's illustrated in these plots on the left. So if we take all the pairs of stations with a 0 to 3 kilometer separation, so we've got to take a little bit of an interval on those separation distances just so we get enough station pairs. But 0 to 3 kilometers, that's plotted here on this left panel. So the x-axis is the residual for one station, and then the y-axis is the residual for the other station that's separate, has that separation distance. So we get the scatter plot, and then we can estimate a correlation coefficient. And we see that these pairs of stations tend to be relatively highly correlated. So if one station has a positive residual, the other station is going to tend to have a positive residual, and similar for negative. Okay, if we go out to bigger separation distances, that's shown on the right scatter plot. Same idea, taking all the pairs of stations 30 to 33 kilometers apart, can plot those. There's still some dependence here, but it's much weaker, and there's much more possibility that one station could have a positive value, the other station could have a negative value, for example. All right, so those are two separation distances. We can keep doing that, and each one of those scatter plots is going to turn into one circle on this figure here. So the horizontal axis here is separation distance. We'll typically denote that with h. So this is how far apart the stations are. The vertical axis is the correlation coefficient. So the blue circles are those estimated correlation coefficients from plots like the previous slides. And we see that at small separation distances, those tend to be close to 1 in correlation. And then as the distance gets larger, the correlation heads down towards 0. There's some scatter in here due to various reasons we'll discuss later. Okay, so once we get some data like that, we can then fit a function to characterize this correlation. So that's shown by this black line here, fitted function. The functional form here in this black line is shown here over on the right. So it's kind of an e to the minus separation distance. And then there's a couple coefficients, C1 and C2, that control the rate of decay as the separation distance gets larger. Okay. And I'm going to call that a traditional correlation model, and we're going to draw some contrasts later in the presentation to some alternatives. Okay, so that's the idea, is that we take all that empirical data, estimate these correlations, fit a model, and then we've got a model for correlation as a function of separation distance. Again, it's stationary, so we only need separation distance to compute these correlations. And then we can use this model for those applications just discussed a little bit earlier. Okay, so that's the basic story, right? We talked about what are correlations, why are they important, and how do we estimate them and build a model that we can use for those important applications. And so if you got this far, you got the basic idea of spatial correlations and ground motions. But there's some complexities with that aren't fully addressed. And so with this second portion of the presentation, I want to get into some of those complexities and some ideas we have about moving forward in the face of those complexities. So let's talk over one of the big issues here. So on the upper right, I've got the map of Chi-Chi, Taiwan, and those residuals that we've been talking about so far. On the left map, this is also a map of ground motion residuals. And this is from a Whittier Narrows earthquake that occurred in Southern California. In these figures, the earthquake locations or epicenters are shown with stars, and then we've got all the recording stations with circles. And if we go through that estimation process like I just talked about and fit correlations as a function of distance to those data sets, we get the results down in the bottom plot here. So we've got distance on the horizontal axis and then this correlation on the vertical axis. And the two data sets produce slightly different correlation models. So both correlations, both lines here are heading towards 0 correlation as the distances get larger, but the rate of heading towards 0 is different. And for distances between, say, 10 and 40 kilometers, the Chi-Chi Taiwan data implies larger correlations than that Whittier Narrows data. And so this type of pattern has been observed kind of for as long as the spatial correlations have been studied. Lots of different folks have reported on them. And there's a lot of different hypothesized explanations for these variability. So one is that there's just regional variations, right? Taiwan is different than California. And so there's differences in the correlations for various reasons. Katsu Goda, Gail Atkinson, and colleagues were some of the early folks to look at this and note that, say, they built separate models for Japan versus California earthquakes. Another possibility here is magnitude dependence. So a large magnitude earthquake is going to have a larger area of rupture. And so that produces a different kind of spatial scale at which the seismic waves are being released and propagated through the crust. And one could imagine that larger magnitude earthquakes, because of that larger spatial dimension of the rupture would have a different spatial pattern of correlations. That's actually been hard to sort out in empirical data, but it's something that's talked about. Site conditions are an important case here. We talked earlier in the presentation about how site conditions are not fully characterized by these ground motion models, and so differences in site conditions could manifest in different residuals and patterns in those residuals. That's been something my group's thought about. Nirmal, JRM, and others, and other researchers have talked about that as well. And then finally, there's this event-specific variability. Maybe we just say, each earthquake is unique, and it's they're all complex, and so the spatial correlations that manifest from those unique earthquakes are going to be different from earthquake to earthquake, and it's hard to predict ahead of time, what those correlation patterns are going to look like. Pablo Jaresi and Eduardo Miranda are recent researchers who've been exploring that idea or advocating for that idea. So lots of different reasons why we might see these differences, and I want to dig into that a little bit because our group's been thinking about it a lot over the years. So how do we dig into this idea a little bit more? So one way that we were interested in, and this was work led by Yilin Chen, was instead of using ground motion recordings where we're data limited, can we use physics-based numerical simulations? And we're not limited by having to wait for large earthquakes. So with this work, we used the CyberShake simulations. Rob Graves and all have been leading this work through the Southern California Earthquake Center. And this is a high-performance computing numerical simulation method where the spatial rupture is characterized as varying in time and space. Then wave propagation through a three-dimensional model of the Earth's crust is performed, and then resulting ground motions at locations throughout the study region are produced. We used the particular version of the simulations we used. There was 400,000 rupture simulations in Southern California. The map of the area where the ruptures is produced is shown down in the bottom. So they have hundreds of thousands of ruptures and then 336 stations, again indicated by the circles in those maps. And so we're really not data limited in this case. We have all these simulations, and some of those reasons for spatial correlations occurring are characterized through these physics-based simulations. So we would hope that we could see some of those manifestations of spatial correlations in these numerical simulations. Importantly, these CyberShake simulations include multiple simulations of earthquakes with the same rupture geometry. So we can actually get repeat observations of kind of nominally equivalent earthquakes where just the timing and locations of the slip are varying from realization to realization. That produces differences in the ground motions in a very controlled manner that we can study statistically. So what do we see? Let me talk you through these plots. The upper left plot is looking back at those traditional empirical correlations like I was talking about in the first part of the presentation. And so what's shown in this map? We've got the map of this CyberShake study region in Southern California. The black lines towards the northeast of the map is the location of a surface projection of a considered rupture. So this is a Southern San Andreas rupture in this case. The black triangle is a reference location that we choose. And then the coloring in the map is the correlation of this is now 3-second spectral accelerations, correlation of those ground motion intensity metric residuals with the reference site. And so we've got correlations plotted just using the traditional empirical model. We're not yet using CyberShake data. This is just a reference case. And so what we can see is that the coloring of those correlations is going from kind of red towards yellow as we get away in distance from that reference station. And these correlations are just decaying as kind of a bullseye. They're strictly dependent on the distance from the reference station. So the further you get from the reference station, the lower the correlation gets, and it just heads towards zero. Okay, so now going to the CyberShake data. This is the simulation-based correlation in the bottom. Got the same reference location, the same considered San Andreas rupture. But this case, what we did is we took all of the San Andreas rupture ground motions and then held that reference site constant, and then picked all the other locations in the CyberShake study area, and we get a whole bunch of paired observations of ground motion intensity. And we can compute a pair-specific correlation coefficient, and that's plotted in this map. So we see a general tendency for a decay from kind of high correlations towards zero correlations as you move away in distance. But there's a little more spatial structure to these correlations now because they're kind of location-specific. We even have some areas where there's kind of light negative correlation between the reference station and those locations. Right? If we move the reference site a little bit in the bottom right corner, we get a little bit different pattern of kind of the high correlations heading towards 0. And we can see hints of what's going on here when we look at the upper right figure, which is a plot of the depth of sedimentary basins in the study area. So there's, in particular, this large Los Angeles basin that's shown by this kind of warm colors. This is a depth down to kind of a stiff soil condition. So there's a deep basin with softer sediments in it right underneath Los Angeles, and that has a tendency to kind of focus or direct the waves that are propagating through the crust. And so we see that in the bottom left, when the station is located inside that basin, we have a little bit higher correlation with other sites in the basin. In the bottom right figure, when the station is moved outside of the basin, we have correlation with the other sites just outside the basin and less correlation with the sites inside the basin. So the common effect of the basin on ground motion amplitudes is being seen here a bit. So we see this influence of these deeper geological conditions that are not typically characterized by ground motion models, or not fully characterized. They are characterized to some extent. Okay, we see some other effects. So here's some other maps of these CyberShake pair-specific correlations. So the left panel, this is now a Puente Hills rupture. You can see the surface projection kind of in the middle of the map. Put the reference site, if we put it right at the south end of that rupture, then all of the other stations that are near the south end of that rupture are very highly correlated with the reference site. The locations on the opposite side of the rupture tend to be negatively correlated. So here we see some kind of directivity or rupture effects here, where when the ruptures tend to be, when they're occurring kind of north to south, all of the locations to the south are going to tend to see stronger ground motion amplitudes, and the locations to the north may see weaker ground motion amplitudes. If the rupture is south to north, then the opposite will happen. And so we tend to see this kind of negative correlation across the rupture, but positive correlation for the sites all in the similar direction relative to that rupture. Similarly here over on the right, we've got another rupture that's heading a little bit off the study area, but kind of all of the locations towards the west, southwest of the rupture are positively correlated, reflecting this kind of common wave travel path from the ruptures. Okay, so there's some evidence from these numerical simulations. Another way we were trying to probe this is to look for some subsets of data that where we do actually have repeat observations from actual earthquakes. So here, summarizing some results. So again, this is Yilin Chen that led it in collaboration with Brendan Bradley at University of Canterbury. So here we took a study area in New Zealand. We did some work in Christchurch, some work in Wellington. I'll show you just the Christchurch here today. But this is an area where there are a lot of repeated observations. So the left panel here is showing the study area. This is down in the South Island of New Zealand. And the stars in this map are locations or epicenters of notable earthquakes, kind of large enough to be of engineering interest, through the 2010-2011 Canterbury earthquake sequence in particular, as well as some other earthquakes that have occurred in the region. That has been a very seismically active area. And it's also a well-instrumented area, as indicated on the right. This is a zoomed-in map of the Christchurch area and the locations of stations that recorded a number of those earthquakes. So there's 26 ground motion instruments we used. So we've got a very nice, rich data set here. And what we did, again, was look at station-specific correlations, where for each pair of stations, we had multiple earthquakes recorded. Not every pair of stations recorded all 25, but there were many paired stations where there was a lot of data of this type. And so rather than having to pool everything by distance, we could look at specific pairs of stations. So what do we see out of that? Well, what we did is we got these pair-specific stations and then did some partitioning into regions. Elin did some statistical work about how to kind of find those regions or neighborhoods documented in the papers. I won't explain that today, but we've got a couple of areas. So if we look to the northwest here, this is an area that's kind of gravelly and relatively flat geology. And so we've got kind of all these pairs of stations here in the northwest. The plot in the top on the right is showing, again, a plot versus distance and estimated correlation coefficients. The black line here is showing one of those stationary models where we just fit kind of all the data and predict correlations as a function of distance. Each circle on this plot is a result from one pair of stations where both of the pair were in the northwest region. And so we've got a pair of stations, we estimate a correlation coefficient, and we know the separation distance between those two stations. So that's the x-axis value. And what we see is that most of these pairs of stations have higher correlations than would be predicted by that stationary model. Not every time, but to a large extent, we see pretty high correlations between these stations, even at larger separation distances. Similarly, we can look at this south region here. This is all stations that are on or adjacent to Banks Peninsula. So this is a much harder rock outcrop condition, and so a different type of geologic condition. If we take pairs of stations that are both within that south region, we can make a similar plot here down on the bottom. And again, most of those pairs of stations have stronger correlations than would be predicted by a stationary model where we just pool all of the data together. And then finally, if we take pairs of stations where one station is in the south region and the other station is not in the south region, and plot those correlations, that's shown in the bottom right, and those pairs of stations tend to have much smaller correlations than predicted by a stationary model. So here, this is showing us some evidence that the geology is really important, and for pairs of stations on similar geologic conditions, they're going to tend to have the same ground motion amplitudes, more so than predicted by these stationary models. And if you move across geologic conditions, you're going to lose that correlation. And so these stationary models might be oversimplifying the effect of some of these phenomena. So that was good empirical confirmation that's consistent with what we were seeing from the numerical simulations, qualitatively at least. Okay, so that brings us to a new predictive model. And so this is work led by Lucas Bodenman. And I want to draw a contrast to that traditional model we talked about earlier, where we have basically e to the minus h as our functional form with that C1 and C2 coefficients that we calibrate to fit those models. So the new model that Lucas proposed is shown down below. I'll briefly show you the functional form, and then I'll show you some interpretations. We've got, so I'll call it rho n for new. We've got that traditional model with the distance dependence. We've got another term with an azimuthal dependence. So this is going to kind of capture some of the wave propagation conditions. And then we've got a third term with a site condition dependence, this rho s. And so that's going to capture the geological conditions. So we're trying to get a model that incorporates those qualitative observations we saw in the last few slides and brings them into a quantitative predictive model. Okay, so let's talk this through with a little more detail. So the left panel here, this is showing kind of a geometric condition where we would want to make predictions of correlations. So we've got kind of a map showing kind of northern easting. We've got an epicenter of an earthquake shown by the star, and then we have two sites that we're interested in, I and J. So we'll take I as the reference site, and we'll think about predicting correlations to other locations, such as site J, but everywhere on the map. So site A and I and site J are separated by distance h. The traditional model is using that h as the predictor parameter. So the right panel here now is showing that earthquake epicenter, the reference site I, and then we're plotting in color the correlation coefficient between the reference site and all the other sites in the study area. So here we get this bullseye spatial decay just as a function of separation distance. So the further you go out in distance, the smaller correlations you predict, and it doesn't matter which direction you go or specifically where those stations are. It just depends how far away they are. Okay, so that's the first term. Now we're going to add to it an azimuthal dependence term. So the extra predictor parameter here, this dA, if we look over on the left panel, this is going to be the azimuthal angle from the earthquake epicenter to the two sites. And so when those two sites are in a similar direction or orientation relative to the epicenter, that dA is going to be small, and we'll use that as a predictor variable. So when we add that in with this functional form, what happens is that relative to that reference site, not all distances are equivalent. So if you move away from that reference site, but in a direction that's heading in the same angle relative to the earthquake, the correlations are higher. If you move in an angle that's changing or move in a direction that's changing the azimuthal angle, those correlations are going to decay more. And so we've got this consideration of shared wave propagation paths in that term. And then finally, we have a site conditions term. So in the left map, now I've added in a coloring that reflects the VS30 values. So we'll use VS30 as our predictor parameter. The site I and site J are going to have different VS30 values in general. And so we'll use this DS parameter as the difference, absolute value of the difference in VS30 values between the two sites. So as that D gets bigger, that's reflecting that the site conditions are different between the two sites. All right? And so we'll have a predictor term that decays the correlation the more different those VS30 values are. So if we use the VS30 values from this map on the left and include the soil condition term in the model, now we have kind of the spatial pattern you can see from the middle map, but now it's broken up by this VS30 difference, where sites with similar VS30 values have higher correlations. Sites where the VS30 value has differed are going to have a decreased correlation. So that's how we can catch these different effects in this single correlation model. So now there's 3 predictor parameters and some extra coefficients we have to fit for the model. So those extra coefficients, though, does raise some questions that we struggled with. In the traditional model, right, we just have 2 model parameters, the C1 and C2. With this new model, we've got kind of 5 parameters to be fit. And there's questions about, could we overfit, and does the extra complexity, is it actually justified by signal we see in the data? So first I want to talk about, a comparison to the broader ground motion modeling world. So these empirical ground motion models have similarly evolved. So one of the earliest models, ground motion models, was by Luis Esteva and Emilio Rosenbluth, 1964. They predicted ground motion amplitudes as a function of just magnitude and distance, and there were 3 coefficients that needed to be fit to that model. This was very early days, very limited data. As data got better, we move into a more refined era. So to take, for example, one of Bill Joyner's models with his colleagues Dave Bohr and Fumal in the 1990s. They added VS30 as a predictor parameter. There is also a rupture mechanism predictor that's influencing the C0 coefficient. We've got kind of extra coefficients, extra predictor parameters, reflecting our better understanding of these ground motion processes and the variables that influence them. So as we move into a more modern era, say the NGA West 2 ground motion models, those are quite sophisticated now. As we move into a more modern era, say the NGA West 2 ground motion models, those are quite sophisticated these days. To take, for example, the Cho and Young's model, this has now got more than a half dozen predictor parameters and more than a dozen coefficients that need to be fit, reflecting, one, a much richer data set that allows us to fit more complex models, and 2, just more understanding of the factors influencing ground motion amplitude. And so as our understanding grows and our data grows, we're able to be more precise with these predictive models. And I think that's a little bit what needs to happen with the correlation models, similarly adding coefficients and adding predictor variables. So the question is, though, how do we justify that, if the data is supporting these extra predictor parameters and coefficients? So what we did to consider this is to use the process that I want to describe on this slide. So we take a set of that data, like the Chi-Chi data, and we fit an event-specific model. Here we can fit that traditional model, for example, fitting the C1 and C2 coefficients. In this case, though, we're going to do Bayesian parameter estimation. And so that's going to consider parameter uncertainty here and reflecting that we don't know exactly the values of those parameters. And so that's reflected by the shaded bands here now, rather than a single estimate of the C1 and C2 coefficients that give us this correlation model. We're going to get thousands of samples of coefficients. And for each one of those samples of coefficients, we get a different correlation model reflected in that band of uncertainty. For each of those coefficients, we can hold out a subset of this data and check the predictive power on those observed ground motions with that particular set of coefficients. And that's going to be indicated by this log posterior predictive density, defined here, discussed in more detail in the paper that I cite here. I'll point you to some more information about that later in the talk. But the point is, for each one of those coefficient estimates, we can go back and check how good did that correlation model fit the data. And we have got kind of a histogram here reflecting the histogram of coefficient values that we estimated in the top figure. And so the thing that's important about this metric is that values to the right indicate a better, closer consistency of that model with the data. Okay, and then the x value here is the mean of this histogram. Okay, so that's kind of the general process. Okay, so we then do this in a couple ways. So we've got kind of the one event, and we can fit that traditional model to the data from just that event and do this evaluation like I just talked about. Alternatively, we're going to take 128 earthquake events from all over the world, and these are earthquake events that have kind of a relatively large number of recordings so that we can try to estimate these correlations out of them. We're going to take all 128 events, pool them into a single data set, and estimate this new model that's got the extra 2 predictor values out of it. And then we're going to evaluate the goodness of that model on one specific earthquake event. So if we do that and test the predictive power on just that Chi-Chi event, so the left case, we are using data from that event and checking back against that event, but with that simpler traditional model. With the right path, we use all 128 events to fit this more complex model, and then we use it to go predict how well it is predicting the correlations present in just that Chi-Chi event. Okay? So in this particular case, the new model is doing better than the traditional model, indicated by this histogram being shifted over to the right. And so now we want to do this kind of across a whole bunch of events and see how we're doing on predictive power. So that's what's shown in this figure here. So in this figure, each circle is one of those 128 earthquakes that were used in the overall fitting. The Chi-Chi event specifically is shown here in this circle. So the horizontal axis of the plot is showing the number of records in that earthquake. So there were almost 400 recordings in the Chi-Chi earthquake. And then the y-axis is showing the relative improvement of that global model relative to an event-specific model. So I'll call the global model the kind of 3 predictor parameter model with the extra coefficients. And then the event-specific model is just that distance only, but fit specifically to that event's data. And so the values that are above 0 says that the new global model is doing a better job of predicting the apparent correlations in that earthquake. And below 0 means that the traditional model that was fit just to data from that earthquake is doing a better job. Okay? So over on the left part of this plot, we see kind of a scatter around 0 and maybe even a few more points below, probably a few more points below 0 than above 0, indicating that for these kind of less well-recorded earthquakes, the traditional event-specific model might be more predictive. But as we get over to the right and more than, say, 200 recordings in the data, the global model is consistently doing better. And that's interesting. So the more data we have from that earthquake, the more clear-cut it is that the global model is more predictive. In these kind of more sparsely recorded earthquakes where we don't have quite the data constraint, we can do apparently better by fitting this event-specific model, but we're testing it on that same data we fit to. And so I think there's some evidence that we're overfitting that traditional event-specific model in this case, right? And so this is kind of clear evidence that the global model is doing kind of better in the best constrained cases relative to those event-specific models. This is all testing back on the specific event being considered. If we think about some future event that hasn't yet occurred, the global model is even more advantageous because that model still works for some unforeseen event. But if we want to think about event-specific models, we're not able to train an event-specific model on an event we haven't yet seen. So in kind of test data outside of the calibration data, this kind of event-specific framing doesn't really work. Okay, so come back to the question I posed in this part of the talk. If we think about that Whittier Narrows and Chi-Chi Taiwan earthquake, and we talked about the differences in apparent correlations from event-specific fitting of traditional models here, and we talked about the possible reasons for those event-to-event variations. What I hope I've shown you is that we're seeing increasing evidence that those differences here are source to site geometry, that azimuthal angle that we were talking about, and wave propagation paths that we saw in, say, the CyberShake data, as well as site conditions. So we saw that in the New Zealand empirical data, and those were those predictor variables that we fit into this global model. And thinking about Whittier Narrows and Chi-Chi specifically, I think there's quite a bit of source to site geometry effect here. So you can see that in Whittier Narrows, the stations tend, and these are both on the same spatial scale, by the way, these two maps. So in Whittier Narrows, a lot of the stations were grouped very close to the rupture, and they're in kind of all directions relative to the rupture. So even pairs of stations that are not too far apart from each other might be on opposite sides of the rupture. Whereas in Chi-Chi, there was a much larger area where the recordings are being taken from. And so two stations that are relatively close to each other may be far from the rupture and may have had quite similar wave propagation paths to them. And so we can see that if we take all the pairs of stations from these two data sets that were less than 40 kilometers apart, which is kind of the distance shown on this correlation plot on the left, and we look at the histograms of this angular distance. So what was that distance between the azimuths? And the Chi-Chi pairs of stations tend to have quite similar angles relative to the rupture, whereas the Whittier and Narrows pairs of stations were much more likely to have angular distances that were much further apart from each other. And this new global predictive model functional form that I have been talking through, that would then predict that many of those Whittier and Narrow sites should have lower correlations because of these larger angular distances. And so what we would argue is that this apparent lower correlations in Whittier and Narrows for a given separation distance is not actually a separation distance effect. It's a azimuthal angle effect that should be accounted for and just isn't accounted for in these traditional models. And so it's not that there's different correlations between these events. It's just that the stations that we used to record those events had different geometric configurations, and that manifested in an apparent difference in correlations. And we wouldn't want to take those apparent differences in correlations with distance and apply them to some new unforeseen earthquake that has, yet again, different geometry from the locations of interest to the rupture. All right, so one final thing I want to talk about briefly is, this refined model with the azimuthal angles and site condition differences, what impact could it have on risk, right? If it doesn't have a practical impact, maybe it's not of a big importance that we think about these extra predictor parameters. So what we did is set up a simple case just to get at the indication of potential risk. This is the San Francisco Bay Area. The left peninsula over here is where San Francisco is. We considered a Hayward rupture indicated by this dashed black line with an epicenter at the south, rupturing to the northwest. And then we took 4 study areas, numbered 1 through 4. And so they have kind of different geometry relative to that rupture, and they have different soil conditions. So the VS30 values are indicated by the coloring. So say study area 1 is down in flatter, softer conditions close to the San Francisco Bay. Study area 2 is getting up into the Oakland Hills a little bit, where there's some harder soil conditions, and so on. And then what we did is we did a set of simulations of potential ruptures, potential ground motion amplitudes, considering either the traditional distance-only correlation model or the new, more refined correlation model. And then we just counted, and let me move over to this upper right figure. So this is a plot for the subregions 1 and 2. We counted across those simulations what proportion of the sites in those study areas had amplitudes of 1 second spectral acceleration that were bigger than 3/4 of a G. So this is kind of how much of the study area had a high amplitude shaking. And in this case, and we ran a bunch of simulations and then just counted up how often that was happening, and made these plots here with the 2 different correlation models. So in this case, the traditional model is predicting it's more likely that we would see high proportion of sites that are higher than that given ground motion amplitude. Right? The new model would say, no, it's actually a lower probability that would happen. And that's because regions 1 and 2 have quite different azimuthal distances azimuthal angles relative to the rupture. So the new model is going to decrease correlations because of that. And also study area 2 in particular has quite different soil conditions within the study area. That's also going to dampen the correlations a bit. And so with the lower correlations, we have less likelihood of large fractions of the study area exceeding some high threshold of shaking. If we repeat the exercise with regions 3 and 4, so there's a little bit more homogeneous soil conditions, also more similar angles from the rupture to the study areas, the old traditional and new correlation models have no practical impact on these proportion of sites that exceed some threshold of ground shaking. So there's going to be some problem dependence on how important these extra predictor parameters are. We were trying to get some indication of this from these simple studies of just the ground motion fields. What we'd like to do moving forward is get back to those infrastructure models where we're actually kind of looking at a more direct metric of impact and trying to understand the role of correlations in those types of risk analysis problems. Okay, so with that, that's the end of the new results that I want to present to you. I want to leave you with a few thoughts about what's coming up in the future and then some concluding remarks. So this talk is aimed at research at the interface of earth sciences and earthquake engineering. I think on the science side, there's some really interesting questions that can now be addressed given recent developments in our field. One is using low amplitude ground motions. I talked about the limited ability of limited availability of strong ground motions, and that's influencing some of our estimation techniques. If we could use low amplitude ground motions, and then moving to the second point on this list, these new technologies, distributed acoustic sensing with fiber optic cables or nodal arrays that can be deployed for short amounts of time to record these low amplitude motions. those technologies can record at much finer spatial scales, can collect a lot more data than traditional strong motion instruments. So if that can help us understand kind of the role of geologic conditions or other factors on ground motion amplitudes, that could be really informative for the science of the future of these correlation models. There are going to be effects of nonlinear site conditions or large ruptures nearby that we wouldn't be able to capture with these techniques, but I think it's worth exploring how much they could inform our understanding of ground motions. The other path forward is these numerical simulations. So we talked a little bit in the talk about the CyberShake ground motions. These technologies are continuing to be refined and deployed in other parts of the world. What I think would be interesting is that the CyberShake simulations I showed you had a fixed model of the 3D crust where the wave propagation was happening through. The extent to which that crustal model has kind of smoothly varying features versus kind of more detailed but spatially variable features in it, that would, I think, inevitably influence the spatial correlations to some degree. And if we can perturb some of those model inputs to understand how they influence the apparent spatial correlations, that could give us a lot more sense of causality, and we wouldn't have to do these kind of inferential techniques that I talked about here. So I think great opportunities on that front as well. On the engineering side, we have some great opportunities as well. So one is to dig in a little more to these refined models and how much practical impact do they have. That's what I just was closing with on the previous couple slides. Understanding when and where they're needed and how much impact they have will help us understand how critical these future refinements are going to be. There are some questions about implementation, data availability. So we do these risk analyses and ground motion map interpolations in software tools. Those tools would have to be modified to some degree to take additional input parameters. There's also questions of data availability. If one of our inputs is these VS30 values, we're going to have that data available to make predictions. Direct measurements of VS30 are oftentimes limited because it's a subsurface condition. They can be inferred from topographic slope indirectly. That's what I was doing in the results I showed you here for the most part. But I think there's a little more investigation we could do into availability of that data and just practical implementation. And then a final area that needs to be looked into a little bit more is multi-intensity measure cross correlations. So it's a topic our group's been interested in and has worked on, but I didn't talk about today. That I showed you results actually for a few different metrics of ground motion intensity, say spectral accelerations at different periods or peak ground velocities or other metrics. Those different metrics of ground motion intensity are correlated between themselves at a given location, as well as correlated across locations as well. And so to get a full characterization of ground motion amplitudes throughout space and across multiple metrics, which is needed for a number of risk applications, we have to build in kind of an extra dimension of correlation into these models. Again, we've looked at kind of the traditional model form with cross correlations. We now have recently released these new model forms, but without the cross correlation. So there's some extra cases that could be considered in that regard. Okay, so start concluding here. I think if I could leave you with one message from the talk, it's that these ground motions, they have spatially correlated amplitudes. Hopefully we saw that empirically from kind of the first slide of the presentation. And importantly, those correlations have practical impacts. All right, so if they didn't have any impact on our work, then it would just be a curiosity, but there are practical reasons for us to be studying these. And so that's why I have kind of presented this set of studies to you. In order to kind of make progress on this problem, we've really used well-recorded earthquakes. We've also used ground motion simulations. Those produce the data that we need in order to measure those correlations, build those predictive models, and then do our downstream analyses. Just like ground motion models themselves, these correlation models need to continue to be refined as we understand the problem better. I think as we move forward, we're going to increasingly use numerical simulations in parallel with observations. The spatial correlations has traditionally been driven by empirical observations, but I think we'll increasingly marry those two sources of data, just like ground motion models have traditionally, or have over the past decade, increasingly used numerical simulations. And I think we need to bring in these additional predictor parameters, as I've made the case here today. We understand that there's path effects, there's side effects on these ground motion amplitudes. Qualitatively, we expect they should influence the correlations. And so the predictive models need to reflect that understanding. And again, this new model form presented here is what we think is the next step in that direction. I don't think it's the last step. We can continue to refine the functional forms, the specific input parameters, but we've set a path forward in terms of what these models could look like, as well as this technique to evaluate, is the complex model an overfit and not justified, or is it actually bringing predictive power to the problem? Finally, I'll point to this website at the bottom, and I'll provide a link in the video description. This is a website that's been put together to host the different papers that I cited throughout the talk, as well as some software tools that can be used to do the estimation of correlations from data, as well as the kind of forward prediction of correlations, both the traditional models and this new functional form described here. And then finally, because this is the William B. Joyner lecture, I want to just say a couple words about Bill Joyner. So he was a renowned seismologist at the U.S. Geological Survey. I unfortunately didn't have the chance to meet him myself personally. He passed away just a few months before I started as a graduate student working in these areas. But I've come to know, through him, through the many Joyner lecturers over the years, and many other mentors of mine throughout my career. Bill was tremendously impactful in bridging the divide between earth scientists and earthquake engineers studying the earthquake problem. He made really important contributions to ground motion prediction in other fields. I mentioned the ground motion prediction briefly in the talk. But I think in an era when he was early in his career, the earth science and engineering communities were not nearly as integrated as they are today. The integration of these communities and the ability to work across disciplines in these set of problems has opened up a rich set of opportunities for me professionally. I've benefited tremendously from this environment of integration, and so I'm really thrilled that the Joyner lecture was established to recognize that kind of work, and I'm really thrilled that I was able to be a Joyner lecturer for the year 2023. I hope with these ideas I've shared with you in this video, I've given you some sense of the potential research opportunities and achievements at this interface. And I think we all have Bill Joyner to thank for the environment that's allowed this type of work to proceed and be recognized. So with that, I'll close. Thank you very much for your attention.